Welcome everyone. This lecture is going to be quite short, and we are just going to look at one specific thing, which is why do we have to do stress transformation? I know that you have not been exposed to this concept before, but this is an important part of this class. We will look at the specifics of how we do what is called the stress transformation in the next lecture. But today I will just talk about why we want to look at stress transformation, or why we want to do stress transformations. Okay. So what is stress transformation? Right? The basic idea is that when you define stresses at a point, okay, you define them with respect to a particular coordinate system. Okay, so in this case, it could be just something like this, which is an XY coordinate system, and it's a 1D or 2D problem. Okay. Now, in some cases, we might want to look at the stresses in a different coordinate system, say X prime, Y prime. Okay, and there are specific reasons why we want to do that. So what I want to do in this lecture is to kind of motivate why we want to look at stresses in more than one coordinate system. What is the reason, right? So let's start with a very simple example. Let's think of the simplest case we can have. Say you have an actually loaded bar, okay, which is applied subjected to forces P on both ends. And let's say we look at a point O, okay, a specific point in the cross section here, okay? And the area of that cross section is delta A. Okay? And this is my x axis, and that is my y axis. Okay? Now, if I take a section perpendicular to the x axis, passing through this point O, then the area is going to be delta A. And we know that in that particular cross section, you are going to only have one stress, which is sigma x. And the value of that sigma x is going to be P over A. Okay? And it is going to be P over A for every point in that cross section, but we are just looking at this one specific point O in that cross section. Okay. Okay. And we also know that all the other stresses are zero. So if I look at the cross section there, let's say it's a circular cross section. Okay, and then this is this point O. Okay, and if I draw a small area around that point O, okay, then I'm going to have a sigma x there, but my tau xy and say this is tau xz, they are both going to be equal to 0. Okay, because there are no internal shear forces in that particular cross section. There's only a normal stress, a normal force. So essentially, you're going to have only sigma x. Okay, so tau xz and tau xy, they are both going to be equal to 0. Okay. Now imagine a different experiment. Okay, you're applying the same force P on the same bar. You're looking at the exact same point O, but now instead of taking a section that is perpendicular to the x-axis, let's say you take a section at some angle, okay, here, so that the normal to that plane is at an angle theta with respect to the x-axis. Okay, and that corresponds to your x prime axis. Okay, so all that you're doing is it's the exact same bar, you're applying the exact same force, you're looking at the exact same point, but instead of taking a cross section that is perpendicular to x, you take a section that is oblique. Okay, so that it's an angle to the x axis. Okay, now it's the exact same body, right? It's the exact same point, right? Now let's try to figure out what is the stress at that point O in this x prime y prime coordinate system, not the xy coordinate system. Okay. Now, if you take a section like that and then draw the free body, it's going to look like that. Okay, I'm just looking at the left segment of the free body, right? You're going to have the force P that is still acting, that's the external force. Okay. Now, to satisfy equilibrium, you essentially have to have two forces in that cross section. You have to have a force along the x prime direction and a force along the y prime direction. Both have to be there. Okay? And the other thing that you'll notice is that this area of the section is not going to be A, it's going to be A divided by cosine theta. Okay, that just comes from the geometry. Okay? So three things are changing, right? Or two things are changing. So instead of having only one force, okay, you're going to have two forces in that cross section, and the area of the cross section is changing. Okay? Now, looking at it again, you can figure out what are these forces px prime and py prime by using force equilibrium. Okay, you can say sigma f, the sum of all forces along the x direction, for example, is 0, and sum of forces along the y direction is going to be equal to 0. And if you write it out, the equations will kind of look like this. Okay, so p plus py prime sine theta. Okay, so these are the forces that are along the x direction or in the minus x direction. They have to be equal to all the forces in the in the positive x direction, which is nothing but px prime times cosine theta. Okay, so that is one equilibrium equation, and you can do the same thing for the equilibrium of forces along the y direction for this free body here. Okay, this is what I'm looking at. Okay, and for that you will find that px prime sine theta plus py prime cosine theta, that should be equal to 0. Okay, now you can solve for px prime and py prime using this equation, but that is not the point here. Now, if you think about what is the normal stress on this cross section, okay, this cross section here, this one, right? The normal force in that cross section is px prime, and the area of that cross section is a prime. So the normal stress along the x prime direction is this px prime over a prime. Okay, and you can verify that px prime over a prime is not equal to p over a, which was the sigma x that we found in the previous case. Okay, so px prime over a prime is sigma x prime, and that is not equal to sigma x. Similarly, the shear stress on this plane is going to be the area, okay, a prime in the denominator divided by py prime. Okay, and py prime is not 0, which means that tau x prime y prime is not 0. On the other hand, for the exact same problem, we found that tau xy is 0. Okay, so which stress is correct? Is tau x correct or tau x prime y prime correct? Because they are not the same, clearly, right? One is 0, one is clearly not 0. Okay, so which one is correct? The answer is both stresses are correct for the respective coordinate system that you have chosen. Okay, so just by changing the direction in which we take the section, we essentially find that you have different stress components at the exact same point, for the exact same body, for the exact same forces that you are applying, right? And both of them are correct. So which particular stress are we going to use to figure out whether this is going to break or not, this body is going to break or not? Okay, we have a problem, right? So the first thing that this illustrates to us is that the stress components that we evaluate at a point depends very much on the coordinate system that we choose for analyzing the problem. Okay. The second thing is, if the stress components are going to keep changing, okay, so I say you and me, we analyze the same problem. Okay, I choose my x to be this way, y to be that way. Okay, you choose your x to be this way, or x prime to be this way, and y prime to be that way. Okay, both of us are going to get different answers, right? How can we determine whose answer should be used for actually figuring out whether this particular body is going to break or going to yield, right? So we essentially need to come up with a measure of stress that is independent of these coordinate systems. And for doing that, we need to be able to transform stresses from this arbitrary coordinate system to specific coordinate systems where things are invariant, things don't change. Okay? So that is the main reason why we want to come up with this idea of stress transformations. So as we go later on in the class, we will look at what are called as principal coordinates. Okay? So somehow you transform your coordinate systems from the given coordinate system to the principal coordinate systems, you get a very specific stress matrix where all the shear stresses vanish. Okay? And you have only normal stresses. Okay? So to accomplish those kinds of transformations, to go from the given coordinate system to a specific coordinate system and then being able to analyze stresses in those coordinate system so that we can determine whether the body is going to yield or break or whether a crack is going to propagate and so on, right? It is very essential that we must be able to transform stresses from one coordinate system to the other. Okay, and that is actually something that will take a bulk of the next 3 or 4 lectures, where we first look at stress transformations in 2 dimensions, okay, which is the simpler case, and then we use those concepts to do stress transformations in 3 dimensions. And then using the stress transformations and stress transformation equations, we will determine what are called principal stresses, principal directions, and the planes of maximum shear stress, and so on and so forth. Okay, so I hope that this kind of tells you or gives you a good reason on why we are going to do stress transformations. Okay, I'll see you in the next lecture. Thank you.